welcome everyone to another one of our seminars. We're very lucky today to have Niall Mac Dowell from Imperial College, and I guess Bay is part-time as well now, to talk about negative emissions, a very interesting area of work. And please go ahead and tell us about negative emissions technologies, BECCS and DACCS.
Thank you very much. So I'm going to talk about bioenergy with carbon capture and storage, so BECCS, and or direct air capture of carbon and its storage, or direct air carbon capture and storage, DACCS. Before I do, I want to just acknowledge my various sponsors, which includes the UKCCS Research Centre, but also the IEA GHG R&D program, Total, and actually I really need to change this because this is now Total Energy, NERC, and EPSRC, and all of these folks have been kindly supporting my work for quite a while, and it's on the basis of all of that that I've been able to come to some of the conclusions and ideas that I'm going to present to you today. So greenhouse gas removal, GGR, where's this all coming from? So a couple of years ago, there was a really useful report by the Royal Society and Royal Academy of Engineering, which sort of pulls some of this together. And the first piece is that following the Paris Climate Agreement, we broadly agreed to try and limit warming to well below 2 degrees and aiming toward 1.5 degrees. And there are a whole bunch of different ways of getting there, but all of them pretty much require the removal of CO2 from the atmosphere, both to offset, so to deal with very difficult or hard to abate parts of the emission portfolio, and then also to just claw back from what is now considered to be, I think, the inevitable overshoot of climate targets. So today, if you combine all CO2 and cement and all sorts of things from fossil fuels and cement production, we emit something like 30, coming close to 40 gigatons of CO2 per year, and then plus a bit more for other greenhouse gases. And that gives you kind of an order of magnitude of the size of the current global economy as well. Now, and again, it's a range, but by the end of the century, so 80 years from now, we need to be removing as much as 20 gigatons per year of CO2 from the atmosphere. Put another way, the GGR removal business, that industry, that whole sort of thing that we need to set up, is going to be comparable in size to the total energy sector today. In other words, it's very, very big. Second point, so you can see that in this example scenario, the world reaches a net zero emissions in 2090. Now, note that this is comparatively late. Most of the IPCC stuff will get you net zero somewhere between about 2050 and 2070. But the point is that regardless of when you get to net zero, owing to the way the rest of the economy works, we need to start removing CO2 from the atmosphere much earlier. And in this example, as early as 2030. So in terms of timing, 2030 is basically tomorrow. We're now basically in 2022. You do not have much time to start doing things if you want to be able to start actually pulling carbon out of the atmosphere in 8 years. So this is really right now. In terms of where, and again, I've missed a piece here, but basically the idea was to look at where what was the application of greenhouse gas removals, and these different colors correspond to different parts of the economy. The small slices at the bottom correspond to residual or fugitive emissions from the industrial sector, the power sector, and so on. And then these larger pieces correspond to mobility, agriculture, and just other what are considered to be hard to abate. The key point is that removal is not an alternative to mitigation. It's not something that we do instead of wind power or instead of carbon capture and storage. It's something we do as well as when we've done as much as we possibly can of all the other things. So just very, very basically, right? So if you think that, and again, this line is a little bit out of date, but it gets you the basic idea. Since, the very beginning of the Industrial Revolution, so this is about when we started burning fossil fuels. We've put something like, well, probably now a little bit more than this, but we put a certain amount of CO2 into the atmosphere, which has delivered a current CO2 concentration of something like 405 parts per million, which gives us, allows us to calculate or approximate a remaining carbon budget. And if you sort of imagine that, and you can tell when I made this slide, it's back in sort of 2017. If you imagine that back then we had just turned around and started sharply reducing CO2 emissions such that we would get globally to net zero by 2050, we would still have emitted more carbon into the atmosphere than our budget allowed, which meant that as a minimum, in order to meet a 1.5 degree target, we would have had to remove this surplus. So that was like the bare minimum. Obviously, this hasn't happened, so we will need to do more. So in other words, the longer it takes us to peak global emissions and then start reducing them and then finally get to net zero, the longer it takes to do that, the more CO2 we're going to have to remove. Just simply, and that's regardless of, that is in a paradigm of mitigating as fast as you possibly can. Just because of the overshoot, you will have to remove some CO2 from the atmosphere. A way of thinking about this could be this sort of bathtub analogy. If you need to, at some point, pulling the plug or turning off the taps is not going to be sufficient to stop the bath from overrunning. And once the bath has overflowed, you're into a situation of having to mop up the floor. So there are many potential pathways, and this is from the IPCC back in 2018. So there are many potential pathways to deliver a sort of 1.5 degree target. So again, this is in a world where in sort of 2020-ish, we're emitting something like 40 gigatons of CO2 per year, or CO2 equivalent per year, and then different ways of getting down. These various pathways correspond to different sort of ideas as to how the world will change and so on. And thus you get into these different balances between what are called a FOLU. So basically this is afforestation and other land use change. And then BECCS. Well, BECCS is sort of a euphemism for any kind of engineered carbon removal. So personally, I think that this first pathway is just fanciful thinking. It's sort of off the table. So if we are lucky, in my opinion, we're into P3, where we will get to net zero globally somewhere in the in and around 2060, and that will be very lucky. If not, you get into P4, and what you can see is the longer that you delay, the greater the ask on carbon removal that you'll have, and also the more challenging this will become. So as I said, GGR is part of the solution. It's not the solution. So, there are many, elements of, well, one big element of causing climate change. That's the way we use fossil energy. And so there are lots of ways we can respond, one of which is, reducing energy demand and doing fuel switching to use renewable energy and so on. We can do industrial level CO2 management. So using CCS technologies on the power and industry sector, as well as CO2 removal. And then you get into this adaptation space, which is something that I'm not going to talk about, but and also RAM. GGR, on balance, it refers to a portfolio of pathways. So there are many ways of pulling CO2 from the atmosphere into different parts of into different carbon sinks around the planet. So, for example, you've got above ground biomass and sort of trees and hedges and so on. You've got soil carbon storage. You've got geological carbon storage. So that would be, again, here for direct air capture and bioenergy with CCS. You have mineral carbon storage. So this is reacting CO2 with silicate or carbonate rocks, and then finding a way to get that carbon into the ocean in some way, shape, or form. What I'm going to spend the rest of this talk focused in on is BECCS, bioenergy with CCS, and DACCS, direct air carbon capture and storage. I'm not, and recognizing that lots of folks here are relatively early on in their journey into the wonderful world of CCS and GGR, I'm not going to spend too much time on the technical details. So I'm not going to tell you anything about the thermodynamic conditions of the A-beam that you use in the direct air capture technology. If anyone wants to know more about that, you can ask me later. I'm going to try and keep this reasonably high level. So one of the key points, and again, starting on sort of basic level, we really need to distinguish between offsets and removal. So there's any amount of, you've got Carney's task force for voluntary carbon markets. You've got these McKinsey reports talking about the billions of tons of offsets and how much it's going to make us, and all these kinds of ideas floating around the place. There are any number of organizations who will sell you an offset, right? A lot of that isn't actually an offset in the context of what we're trying to achieve here. So if we think about, the world today, we're we're positively emitting CO2 to the atmosphere. And the objective is to get, for the UK, to net zero by 2050, and presumably continue the journey perhaps to net negative in the second half of the century. So when we start removing CO2 from the atmosphere in, as discussed before, the 2030s, the objective is to get to a place where in the period between 30 and 50, we have scaled up carbon removal such that removal activity in 2050 balances or offsets residual emissions in 2050 such that the net result is net zero. So whilst gross emissions to the atmosphere may be positive in the UK in 2050, we will also be doing sufficient removal activity to offset those gross positive emissions such that the net result is zero. Okay. Thereafter, we would hope to continue to reduce or to decline the positive emissions of CO2 and other greenhouse gases to the atmosphere, whilst simultaneously increasing or continuing to increase the amount of greenhouse gas removal activity, such that we then spill over later into a world of of genuine removals, resulting in negative carbon balance for the UK. So what's also really important is that from the climate perspective, the purpose of doing this is not to meet some kind of short-term target. It's not to sort of solve a problem for today and have to deal with it again next week. The purpose of this is effectively climate repair. In that context, temporary removals do not solve this problem. So this is a fairly complicated graph, which basically shows you the impact of, so if we emit some CO2 today, so 800 gigatons or thereabouts, which results in a CO2 stock in the atmosphere. And then the question is, if we temporarily delay, so for example, if you were to delay that emission by 100 years or 300 years or 1,000 years, what difference would that make to the peak CO2 in the atmosphere? So in other words, how much warming do you avoid? What you can immediately see from this is that whilst a temporary removal of, say, 100 years has some climate benefit, it doesn't solve the whole problem. So if you do something that removes CO2 from the atmosphere for, effectively less than 100,000 years, you haven't actually done the thing that you're setting out to do. So we need to bear this very carefully in mind when we're thinking about comparing the price of, for example, pathways towards soil carbon storage or afforestation versus the cost of permanent carbon sequestration in the subterranean geology. I'm not going to go on about this anymore, but permanence is really important. And being able to demonstrate that is also really important. So what is greenhouse gas removal? So the ZEP, and I've neglected to reference them here, but the EU's zero emissions platform, they've come up with these 4 principles that need to be abided by in order to deliver a GGR project. So the first is that CO2, carbon dioxide, needs to be physically removed from the atmosphere. So that's number 1. Number 2, the removed CO2 is stored out of the atmosphere in a manner intended to be permanent. Next, up and downstream GHG emissions that are associated with the removal and storage process have to be comprehensively estimated and included in the overall emission balance. So it's not just about what happens at the point of removal, but what happens across the entire life cycle. And finally, obviously, it's important that the total quantity of CO2 that's removed from the atmosphere and permanently stored must be greater than the total quantity of CO2 emitted to the atmosphere in this process. Okay, so it's possible, for example, to remove a ton of CO2, emit 900 tons in that process, and you have net removed 100 kilos. That's still greenhouse gas removal, albeit not terribly efficient. So just some graphics in here. Again, I have properly referenced ZEP here. We can see the difference between removing CO2 from the atmosphere, where you've got CO2 in the atmosphere. It's translated into biomass, for example, transported to a BioCCS facility, and that carbon is securely stored. That's removing CO2. where you remove CO2 from the atmosphere via, for example, direct air capture, use that to produce synthetic fuels. That fuel is then burned in an airplane. That carbon goes back into the atmosphere. That's not removal, that's using CO2. And then finally, we have CO2 from the geosphere or the lithosphere. So this is fossil carbon. We extract it in the form of coal, oil, natural gas. We combust it and capture the CO2 somehow, so probably not in the context of oil. And then we store it again. This is not removal, this is avoiding CO2. So only one of the three. And again, this might seem a little bit obvious, but you will be amazed at the number of meetings that I attend where people are trying to claim that this avoided CO2 or this use of CO2 is basically the same as removing CO2 and should therefore be counted as such. So in order to deliver a project, so if we want to go and do a GGR project, we need to know a few things. So first of all, because basically we're not going to do this as a sort of philanthropic charitable service for free. We're going to want to be paid for the service of CO2 removal. So we need to know when the removal starts. So when are you actually removing CO2 from the atmosphere, which can be very, very different to when you start spending money and doing things. We need to know how much CO2 gets removed, at what rate, and for how long. So that way we can figure out, okay, so how much CO2 have we removed in total? And then finally, we need to know when the project gets concluded. When can I, as a project developer, say, okay, I'm done now, I'm moving on. In order to do this, we need thorough up and downstream life cycle analysis to understand potential sources of carbon leakage across the GGR value chain. Some of this can get very complicated, but it's just unavoidable and it's just something you cannot do without. We need to also baseline background carbon or carbon dioxide levels in a given sink. And this will necessarily vary depending on the GGR approach that's being employed. So for example, if you're doing soil carbon storage or biochar carbon storage or enhanced weathering carbon storage, we need to think about all of these things. And then we need to develop some project completion and abandonment protocols, as well as an MRV, so that's monitoring, reporting, and verification, an MRV plan, and that plan will be revised and updated as the project progresses. So it's not trivial. So bioenergy with CCS. So as I'm sure you know, CO2 comes from the atmosphere, and as we grow primary crops like miscanthus or poplar, in addition, you've got wood residue from forests and so on. You've got crop residue, you've got waste wood from the construction industry, you've got MSW as well. So there are many different ways of getting biomass, which will have taken carbon from the atmosphere. So lots of potential feedstocks. What we need to do is aggregate them and transport them to a sort of a pelleting facility. So as you can turn all of this feedstock into a fuel grade pellet, which we can then transport to our conversion facility. So what you can do here is you can just, thermochemically convert the biofuel to electricity in a straightforward bioelectricity facility. You can do that in a CHP, a combined heat and power, or a cogeneration plant, so you get heat and power services. You could turn it to hydrogen, or you could transform it into biofuel. So lots of things you can do, and all of these things, all of these processes are effectively BECCS. What changes is obviously the cost, but also the balance between energy service provided and carbon removal service provided. And then what you need to do is take the CO2 that you've produced, capture it, and transport it and store it securely. So system dynamics are really important. So depending on how you operate this process, because as you're growing your biomass, you've got a carbon flux. It may require some water, depending on some positive addition of water, depending on where you are in the world, and it also requires some work. So, for example, pesticides, fertilizer, the act of planting itself, all of this requires work and can result in carbon leakage. We need to harvest it and process it, which means drying. Drying often can be just stacking it for a while, but it can also include drying in an oven, which typically runs on natural gas, or can run on natural gas. And again, more carbon leakage. We transport it, potentially more carbon leakage, until we finally have a fuel grade product that we can burn, which allows us to produce power but can also require some CO2 and may also leak some carbon as well, because you don't typically capture 100% of the CO2. So these system dynamics are really important. And for anyone who is interested, there's a paper from 2017 where we go into this in quite a bit of detail. What this means is that for a given, so just because you have a BECCS facility where you're taking CO2 from the atmosphere, all of the choices that you make across the BECCS value chain really impact when you start removing CO2 from the atmosphere and how much CO2 you will remove over your entire lifetime. So depending on choices that you make at the beginning of the project, you can incur more or less carbon debt. So for example, in this scenario, we're planting miscanthus in Brazil. And in order to plant it, we've had to, we've decided, I think here it was changing some kind of land use change. This is relatively benign, up to something here where you were effectively chopping down the rainforest. So these are choices that one will make at the beginning of a project. And it's, obviously from a regulatory or from a policy perspective, we probably want to avoid a world where you're, incentivizing any of this kind of behavior. What you can then sort of define is a carbon break-even time. So how many years does it take you before you've paid back your carbon debt? And you can see that, simply if we're just incentivizing people to remove CO2 from the atmosphere and we have our MRV protocols in place, it will rule out all of this stuff, because nobody wants to wait 10 years or 15 years to get paid for something when you're incurring all of the OPEX of running a BECCS facility for that period. But it's also possible to do it such that you're removing CO2 pretty much immediately. And if you're taking your CO2 from an established forest, as is currently the case, if you're taking your biomass feedstock from an established forest, this initial carbon debt is essentially zero. But the key point here is that, depending on the choices that you make around the fertilizers that you use, the transport fuels that you use, the chemicals that you use throughout the whole process, this really affects everything. So we need to think about this very carefully. Again, what's the water balance? What's the energy balance? There's no single answer. And that's really the one thing that I want you to understand from this. A BECCS plant in Louisiana using miscanthus, and a BECCS plant in Louisiana using willow will have massively different water uses. So that's the color of this symbol. So miscanthus in Louisiana doesn't use all that much water. Willow uses quite a lot of water. But the amount of land, and again, the amount of land that they use, so the symbol of the size of the symbol corresponds to the number of hectares. So for example, a dot about this size is the number of hectares to remove, I think this was 50 megatons of CO2. And again, the same plant removing the same amount of CO2 could use millions of hectares if you make the wrong choice, right? Similarly, broadly speaking, you will be energy positive. So over the whole supply chain, you'll be producing more energy from electricity than you will have used. But it's also possible to make sufficiently silly choices that you would be on balance energy negative. So again, these are the kinds of things that we want to, be a bit careful and avoid. So if we then think about, and this is an illustrative example of a UK BECCS project that happens to be located somewhere in the Northeast, using biomass that's imported from the USA. Here we're assuming 98% CO2 capture on the basis that we want to maximize the CO2 removal that we possibly can. And you're looking at all the points along the way where you're leaking carbon, right? So for example, and you can see that the biggest source of leakage is the way in which we dry the biomass. 5.6% of carbon is lost there. Importantly, and you can see here, there's much more carbon lost from the drying step than there is from transporting the biomass across the ocean. Okay, so ocean transport is not that big a deal. If we reduce the capture rate from 98% to 90%, the 77% number would be reduced to 70. Okay, and we perform this calculation with a tool that my group has developed that we call the Monet framework. On balance, I think that the range of likely carbon removal efficiency, so this is the tons of CO2 removed per ton of CO2 injected, it's probably somewhere between, say, 65, high 60s, and low 80s in terms of carbon removal efficiency. So when is a tree like a barrel of oil? And I sort of want to speak about this a little bit, just on the basis that we hear quite a lot of, well, frankly, hysterical, in my view, narrative around how we're chopping down trees and burning them in power stations, and this is really terrible. And to me, this is sort of like saying, okay, yeah, and when people take oil, they go and they get a barrel of oil, and then having gotten the barrel, they then upend the whole thing into a ship or something and just burn it as, you know, marine crude. That's absolutely not how oil works, and it's not how forestry works either. So when you have a barrel of oil, you produce many different products, mostly fuels, but other things as well, like plastics and chemicals and so on. Similarly, when you harvest a tree, so for example, from the US South, the different parts of the tree have massively different values. And so, for example, the large dimensions, these pieces at the bottom, sell pretty high values, and this is what's used in construction and so on. Pulpwood is the piece in the middle, and this, you know, this is what goes into pulp and paper. And then the low grade stuff, so this will be the branches and tops and so on, sawmill residue. This is very low value, and this is what we, you know, think about using in terms of as a feedstock for BECCS facilities. Importantly, the people who own these forests, they're trying to operate or to manage the forest to maximize their own income. So they are absolutely not going to forego $20 to $50 a ton and sell it to somebody who will only pay them $1 to $2 per ton. That's just not how this works. So effectively, trees are distilled into various fractions. So I stole this slide from one of your colleagues, Carly. We presented this to number 10 a couple of weeks ago to kind of explain this point. So again, saw logs, not used in DACCS. They're high value, they're large, they're straight. This is what you see, for example, if you ever go for a walk in a managed forest, sometimes you'll see pieces of land being cleared. This is stacked up. These are stacked up, and this is what you see. Pulpwood, so this then goes to the sort of pulp and paper folks with 21%. That goes to pulp and paper, as I said. And then this is sort of the rest. And this is what gets turned into fuel grade material. So what's really important is that when we're thinking about sustainable biomass, we need to kind of distinguish between the wood and the trees effectively. And what I mean here is that, so if we think about since the 1950s in the US South, they've maintained this green line about 82 million hectares of land under forest. So the amount of land that's being used as a forest, that stayed constant since the 1950s. In that period, the standing inventory, so you can think about that as the number, the number of trees or the cubic meters of trees or the amount of carbon in that land, has gone from about 5 billion cubic meters to over 10. So it's more than doubled. Okay, so same amount of land, double the amount of trees, double the amount of carbon. And at the same time, they very significantly increased the annual harvest. And again, this varies obviously as a function of demand, but the same level of land producing between 142 million cubic meters of wood to up to 272 million cubic meters of wood. So we can absolutely, through, this is in the interest of the people who own and operate these forests, they maintain the amount of land that they have, because this is their asset. They increase their standing stock of carbon or their number of trees, and also pull out more and more biomass supply. So forest management is complex, but it can be done. So another way of thinking about this, and I'm a chemical engineer, so this is the way my mind works. It's like a batch reactor. So, we're putting in our various feedstocks, so, CO2, saplings, and so on. You're maintaining a constant level of, in this example, carbon in your forest, a number of trees, but you're also at the same time continuously removing products from the reactor. So it's not one tree in isolation, it's a dynamic system. The only thing I really want to say here is that I'm probably quite alone in this in many respects, but I think algal biomass is highly promising. It's very low TRL, but the potential yield from algae on a tons per hectare level leaves forest biomass standing still. And a lot of private organizations are looking at this very carefully. So what does BECCS cost? Well, the short answer is don't really know because nobody's properly doing it yet. Slightly longer answer is it depends on where you are in the world, what's the value of the electricity supply, where do you get your biomass, what does that cost, and so on and so forth. It varies. It's likely to decline and so on with time as we do some learning. But the key point that I want to get across in this slide is we need to distinguish quite carefully between the cost of CO2 stored, the value of the electricity produced, and the value of the negative emission credit, the NEC, that a BECCS plant might produce. Okay, so direct air CO2 capture and storage. So here, we're taking CO2 out of the atmosphere through some kind of process, which we then, where we then process a sorbent or a solvent of some kind. This requires quite a bit of energy input onto the dilution of CO2 in the air. It's very dilute relative to other point sources. And once we have that source of CO2, we then transport it, so that could be by a ship or a pipeline, and put it into a CO2 storage facility. This is eminently doable, and people are doing it today. So to say that it's in any way pie in the sky or something is just a silly statement. It exists. In some senses, it's much simpler than BECCS in that you only need to know what's the carbon intensity of the energy that you're using to run the thing, and you can calculate your carbon balance. So it's very attractive in its simplicity. There are some narratives that would argue that it can go anywhere. I think that's probably not true. These will be big, they will be large facilities. If you want to capture 1 million tons of CO2, which is sort of like your lower bound for a useful facility size, in my opinion, you will need to handle several billion tons of CO2. So you're talking about, you'll need to handle several billion tons of air to achieve it. So this is not something that you do anywhere. It's a large integrated facility. It needs utilities, heat, power, all that kind of thing. You need access to CO2 storage, either a pipeline or a transport facility. So this is not anywhere on the planet. It's more complicated than that, but it can be done. So just thinking about DACCS for a second, and there's a lot floating around, and certainly as John mentioned incorrectly, it's a comment in bays, and I want to hear quite a bit about what price direct air capture is and how cheap it can get, and so on and so forth. So this morning, just before this talk, I went to the Climeworks website, looking at what they're offering today. So £44 a month will get you 600 kilograms of CO2 in a year. So that translates into £880 a ton, or about $1,200 according to XE.com at today's prices. So direct air capture costs us $1,200 a ton today. We don't know on this basis. We don't know about the system LCA, so we don't know about the carbon intensity of the energy that they're using to run this. I mean, I'm sure that one could have gone through that website in a bit more detail than I did this morning, and maybe find some information on this. But we know that it's about $1,200 per ton of CO2 captured, which is not necessarily the same as the cost removed. So any carbon in that energy will need to be accounted for, which will in turn increase the cost of the removed CO2. So what we've been doing in my group recently, I'm not going to go into this in too much detail, but basically we've been doing some work trying to think about, what the cost reduction trajectory of a Climeworks type facility might be, based on, amongst other things, the original patent for the technology, and a bunch of modeling. So obviously take this with a bit of a pinch of salt because it's modeling, it's not real world information. But what we effectively did, is to say, well, what happens if in a world where these Climeworks modules are being mass produced, and you can look at what you need to run the thing, which is, a box and a fan and so on and so forth. And you're effectively saying, and by box, I mean the chassis, which is equivalent to the kind of chassis that you would have with a Volkswagen Golf or something.
So when all of these component parts are at the same kind of cost level as a mass-produced car, which is, we have all the things that we need in a car that we need to make a DAC plant. What might that cost? And we want to run this using renewable energy so as to avoid any kind of carbon leakage. So what we get is the global performance. It varies significantly around the world, as in line with just the variability of the availability of renewable energy. You'll know that the lower bound on this color bar doesn't approach any of the very low numbers that we see sometimes quoted in the media, and the upper bound is still quite significant. So, and this is the cost of the widget, the DAC module. It doesn't include all of the kind of balance of plant piece that we might need to worry about in massive detail. We did our best. What is interesting is that these sorbents, they also remove CO2, whilst removing CO2 from the atmosphere, they also remove water from the atmosphere. So just this water in the air also bonds. And so the amount, and in some parts of the world, and in particularly places like the tropics, for example, Brazil and so on, the co-production of water might actually be quite a useful thing to consider. So just moving on from there. So some conclusions and final slides. So GGR is not an alternative to mitigation. It's emphatically an end-to-end. And how much we need is going to be a function of how late we properly start mitigating and driving down emissions at the global level. I haven't gone into this talk, I haven't gone into anything about who will need to do what and where responsibility might lie and what will be fair. Well, basically, that's a separate talk, but it's an interesting conversation. There are a portfolio of GGR options, and they all have their own unique characteristics. So no one is a silver bullet. We will likely need something of a portfolio, although some things will go earlier, some things will play a larger role, and so on. In terms of climate repair, the permanent removal of CO2 is key, and MRV, the monitoring, reporting, and verification of those removed emissions, that's essential. We need crystal clarity on taxonomy. So removal is not the same as use, is not the same as avoidance. Some more conclusions. So it's entirely possible to deliver sustainable biomass at scale. It's also entirely possible to very badly mess this up, and that's definitely what this stands for. Nobody wants to burn whole trees. That's just insane. With BECCS, you also need to think carefully about the value between. You need to distinguish between the value of dispatchable power and a sensible counterfactual. And so, for example, if we agree that bioelectricity is a form of renewable electricity, then a counterfactual could be what would be the value or the cost of wind plus a synchronous compensator to provide good services plus energy storage to provide some firming capacity, and the value of permanent and readily verifiable carbon removal. So a counterfactual there could be direct air capture. The cost of BECCS, well, we don't really know yet. It'll vary as a function of location, and then see the way in which the biomass supply chain is flexed and evolves will also impact things significantly. And biomass price hedges will be really important. The UK is potentially a good place for BECCS, as there is an established biomass. We already have lots of ships. Most of the ships in the world with biomass are coming to the UK. We've got good potential to increase domestic biomass supply. And we also have excellent CO2 storage potential in the North Sea. And personally, I think that the UK could and should develop this and seek to provide removals, whether they come from BECCS, DACCS, whatever. We've got an amazing CO2 storage potential in the North Sea, and we could seek to provide removal services internationally. That's some more conclusions. So just on BECCS, I don't really want to say too much. I think it's an early stage or pilot scale technology. It's certainly interesting, but I don't think we know what it costs. According to websites, it costs more than $1,000 a ton. I think pathways to cost reduction remain uncertain, and this is again my analysis, it's probably wrong, I'm sure we've made mistakes and so on, but I think that I don't see how low prices that are being promised arise. I don't see how you get cheaper than a mass-produced car for the various bits and pieces. So maybe there's an alternative. And we were very bullish on the price we assumed for the actual sorbent material in there. But I do think that there is a potential for the co-production of water and CO2, which could be interesting in some parts of the world. So with that, I'll end, and I'm happy to try and take any questions or comments if anyone has any. Well, thank you very much.
Thank you, Niall. So I don't have any immediate questions that I can see. Maybe I'm missing something, but just on that last point, you're comparing the cost of a mass-produced car, or looking at the cost of mass-produced car for Climeworks, which I agree is a reasonable analog. But what about something like carbon engineering, which is arguably more in the coal-fired power plant sort of league, where you've got a big central thermal processing station powered by fossil fuels? And I don't see why you can't use fossil fuels to power DACCS if you've got carbon capture and storage on it, obviously. And then you've got the solvent, or the regenerated solvent, going to, yes, a large number of cooling towers, which are still a bit more than the car class of sort of mass production.
Yeah. So the bit that I didn't show is that we first of all did a fairly standard exergy productivity analysis, which, and again, just simply owing to the quality of energy required to run carbon engineering type project. So you need heat at sort of 1,000 degrees Celsius or thereabouts. So yeah, you could be burning some kind of fossil fuel or hydrogen or something to get there.
Yep.